turn to some interesting solutions of the Schrödinger equation for fairly simple potentials. Let's begin with the case of a barrier at which the potential changes abruptly to some value larger than the kinetic energy of the particle. So for example, this could be a region where suddenly the electron sees a negative charge and would be repelled by it because its potential to the right of x equals 0 is greater than the kinetic energy, and so the electron would not be able to penetrate into that region. That's of course classically, but remember we have to solve for the quantum mechanical case. We can do this by recalling the solution on the left of the barrier, which was a exponential wave with the wave number being given by this expression. Now to the right of the barrier we can use exactly the same function. That will satisfy the requirement that the wave function and its derivative just to the right and left of the barrier be precisely equal if we use the same function. But there is a trick here. If we do use the same function, notice that this term e minus v on the right of the barrier is negative because v is greater than e. So if we take the minus sign outside the square root and define kappa to be the square root of 2m v minus e, which is now a positive number, we have a wave function identical, of course, to the wave function on the left of the barrier, but one we can write out I times I being minus 1 as e to the minus kappa x. So on the right of the barrier, what was an oscillating wave function becomes an exponentially decaying wave function. This is the origin of the phenomenon of tunneling. So shown here is a freeze frame of the wave function at some point in time. Of course, the wave function and its derivative are continuous across the barrier. But once the one looks to the right of the barrier, the probability of finding an electron falls like the square of the wave function, or as e to the minus 2 kappa x. Now we will see later that 2 kappa is on the order of an angstrom for an electron trapped within a typical metal. So the probability of finding an electron outside of its home in a metal is very small indeed. This phenomenon is referred to as tunneling. Now the electron is not actually tunneling through anything. Remember, we are just calculating the probability of finding an electron somewhere, and quantum mechanics says that outside of a barrier like this, there is some probability that on repeated measurement one will find the electron to the right of the barrier. This probability is given by an exponential decay with a decay length of 2 kappa. So this is an important result, the basis of the scanning tunneling microscope, and one we will talk about a lot more in subsequent chapters. Another important simple tunneling problem is that of a particle trapped in an infinite potential well. Now we use an infinite potential well purely as a calculational simplicity. The reason we do this is that if the potential outside of the box is really infinite, then the probability of finding an electron outside the box has to be 0, and therefore the wave function has to be 0 outside the box also. And this means therefore that at x equals 0 and x equals L just inside the box, the wave function must also be 0. So we cannot use our exponential function here. We need a function that goes to 0 at x equals 0 and x equals L. One function that does this is the sine function. Providing we choose the right value for this parameter k. In fact, it's simple to see that as long as we have k being equal to n pi on L, then this function indeed will satisfy the boundary conditions. But notice this is true of any value n equal 1, 2, and so on. And so we can put successive sine waves in here just so long as they go. So here is n equal 1, n equal 2, n equal 3, and so on. So there is in fact an infinite series of functions that satisfies these boundary conditions, and they are, when normalized by integrating the square of the function and setting it equal to 1. That is a homework problem which I suggest you carry out for yourselves. We find the value of b, and then substituting the value for k, we have n pi x on L as the argument of the sine wave. So these are the allowed states of the electron in the box, or the particle in the box. These are called the Eigen States, with the wave function being the corresponding eigenfunctions. If we substitute these eigenfunctions into the Schrödinger equation, so we simply take the second derivative, put it into the Schrödinger equation, immediately we obtain the result that the energy is given by h bar k squared over 2, or you use the result, I'm sorry, that the energy is h bar squared k squared over 2m. We could have gotten this result by substitution into the Schrödinger equation. We end up with an expression for the energy that is given here, n squared h bar squared pi squared over 2ml squared. So the energy goes up like n squared, so the higher the eigenstate, the higher the energy. So the ground state energy of the particle would be h bar squared pi squared over 2ml squared. The first excited state would then be 4 h bar squared pi squared over 2ml squared, and so on. So these are the series of allowed energies in the box, and clearly the gap between the ground state and the first excited state of the system, I equal n equals 1 and n equals 2, varies like 1 over L squared. This is the origin of the phenomenon we introduced in Chapter 1, where making a particle smaller increases the gap between the ground state and optical excited state, so that as quantum dots are made smaller, their fluorescence goes to ever shorter wavelengths. So a very important result to remember then is this expression for the energy of a particle in a box, n squared h bar squared pi squared over 2ml squared, 1 over L squared dependence of the energy on box size. And remember also that there is an infinite series of eigenstates that satisfy the boundary conditions imposed by this infinite-sided box.